Hi and a very good day to everyone. Okay, today I would like to present about the lab, which is the topic is friction losses in pipes. We are a group of 3 members and I am Satyara Ramalu and from group 3. Okay, first we talk about the background. Okay, this experiment is analysis about the fluid flow in a pipe network and investigate the multiple methods for calculating the fluid flow rate. And from that we can know about the effect of the screen friction, pipe network design, pipe fitting, and also the pressure drop through a pipe. Okay, then the fluid flow rate and the fluid flow network configuration are the major independent variables in this experiment. And they got some factors for frictional losses, which is caused by the frictional losses are determined by the flow condition and of the physical properties of the structure. And second is the flow fluid molecules in opposition to one another. And third is the movement of the fluid molecules against the inside surface of pipe or the similar structure. Okay, next I would like to talk about the frictional losses in fittings. From that we can calculate to get the friction losses, which by the using factor kf, and w loss equals to kf times of v square over 2. Then you will get the w loss. And next I would like to talk about the problem statement. In this lab we get a one problem statement, which is to determine the systematic fluid flow analysis. And next they got the two objectives for this report, that is to establish a systematic fluid flow analysis methodology and determine the major and minor losses in multiple piping systems. And next is to study and velocity of the various pipes diameters. And also they got three scopes for this lab, which is to understand the operating system fluid flow, an experimental study of the velocity of the various pipe diameters, and also finally to
Hello, Assalamualaikum. My name is Emir Isha bin Isha Mukri. My ID is MA17235 and I'm from Kuantan. So in this experiment, I'm going to talk about theory first. So when performing the experiment for friction losses in pipes, the Darcy-Weisbach formula for energy equation are used. So this is the equation. Once we cancel out V1 and V2, Z1 and Z2, from here we can find the head loss. So head loss is equal to P1 minus P2. Those are pressure and they're divided by Y, which is a constant. So head loss is the frictional loss in the pipeline that is expressed in the form of a fraction with the available head. Water flowing in the pipeline will experience pressure depreciation due to friction. There are two types, major and minor. So, okay, in this experiment, we'll be focusing more on major. Here, I had lost major. So, these are the uh, these are the points needed to calculate head loss. The F, the D, the L, the V, and so friction factor calculation. So friction factor, there are three types. So for Reynolds number below 2000, we use this normal calculation. For the Reynolds number between 2000 to 4000, we'll use the Colebrook equation. And for Reynolds number between 4000 to 10,000, we use the Blasius equation. So Reynolds number is referred to as the ratio between the initial forces to the viscous forces. So to calculate the velocity of the fluid flow, we have to find the volumetric flow rate, Q. Then we can find the volume of water, which we can find either volume, then we find Q. It doesn't matter. Okay, these are the equation. So these are the apparatus for our experiment. First is the fluid friction apparatus, the hydraulic bench, the pressure sensor, and the data measurement and data acquisition. we also include a stopwatch in this. So in the fluid friction apparatus alone consists of a pipeline flow rig with pipes of different diameters, a tank that is used to measure the water volume flowing out of the system, and a pump that is for refilling the water reservoir. So experiment procedure. All the valves are open to ensure all pipes can flow water. The pumps are turned on to flow the water across the pipeline in the fluid friction apparatus. The control valve is adjusted to see if the volume flow of the water reacts with the adjustment. The tank is observed to see correlation between the control valve and the volume of water flow. To begin experiment, unused valves are closed, leaving the valve across the pipe along which the friction loss can be calculated. So pressure sensors are added to the valve to measure and record readings of pressure P1 and P2. A flow rate indicator is present in this experiment, showing the results in LPM unit. So after we record the first experiment, we can repeat the above procedure for a new value of flow rates. We can repeat getting P1 and P2, and then after doing that, we can start with a new valve. We can repeat the above procedure on another pipe for the second experiment, and so on. So that is all from me. Thank you very much.
Okay, Assalamualaikum and a very good day. My name is Muhammad Najari bin Sufyan and my ID is MA17230. I came from Pahang. Okay, now I would like to explain about the chapter 4, which is result graph and discussions. First, we go to the calculation formulas. Okay, this is the example formulas that we use in order to calculate and get the data. Number one is flow speed, which is we use the formula V equal to 4Q over pi d squared. Next one is Reynolds number. We obtain the Reynolds number by using this formula. The dynamic viscosity we use here is 0.89 times 10 power of negative 3. And then from there, we can calculate the friction coefficient. For the measured friction coefficient, for the calculated friction coefficient, we can use the Colebrook equation, which is this one. And then for the measured friction coefficient, we can use the Darcy-Weber theory, which is this one. Okay. Next is the head loss. For the calculated head loss, we also use the formula from Darcy-Weber. Then we go to the sample calculations. So the given data is length of the pipe, which is 800 mm or 0.8 meter. The diameter, the given diameter of the pipe is 20 mm. The thickness of the pipe is 1.5 mm, and we assume that the surface roughness is 0 mm. Then the sample calculation for the straight pipe. Okay, from the velocity value, we get 0.5796 meter per second, and from there we can calculate the Reynolds number, which is by using the formula given, we obtain 13024.7191. So for this number is greater than 4000, it is considered as turbulent flow. From the Reynolds number, we can calculate the friction coefficient. So for the calculated friction coefficient, we obtain from the Colebrook equation is 0.02219. And then we can obtain the measured friction coefficient, which is 0.1317 by using the Darcy-Weber equations. We also can obtain the calculated head loss by using that particular equation, and we obtain 0.0152 meter. Next, we go to the results. So for the here is the table for straight pipe. In the table, we have the volumetric flow and also measured head loss. For this value or this data is already given in the experiment by using the equipment setup. So we just have to find the measured friction coefficient, velocity and also Reynolds number, and also calculated coefficient friction as well as calculated head loss by using the formula. Next, we go to the graph. So here I provide the straight pipe graph of head loss versus velocity profile. Okay, for this graph, as you can see, for the blue line is considered as measured head loss. It increase steadily as the velocity increases. However, for the calculated head loss, it increases rapidly in the beginning and then steadily as the velocity increases. So what we can conclude here is that the head loss is directly proportional to the velocity of the fluid in the straight pipe. Next, we go to the coefficient frictions versus Reynolds number. So for this graph, the blue lines refer to measured friction coefficient, and the red line refer to the calculated coefficient of frictions. For the blue line, it decreases rapidly in the beginning and then steadily at the end as the Reynolds number increases. For the calculated coefficient of frictions, it decreases steadily as the Reynolds number increases. So therefore, the coefficient of frictions depend on the surface roughness and also internal diameter of the pipe. We can conclude here that higher surface roughness and internal diameter of pipe leads to the higher coefficient of frictions. Okay, the last one we go to the chapter. So as the conclusion, the result obtained from the experiment showing that there is some difference between theoretical and experimental results. So based on our assumptions, there might be an error due to the equipment failure and also less efficiency of the pressure sensor. Based on the data obtained from the experiment, which is measured head loss and also volumetric flow rate, the maximum calculated head loss is 0.1121 meter for every type of parts. So we can see that all graph of head loss versus velocity and friction coefficient versus Reynolds number, they are mostly similar. This is due to the same internal diameter and also length of the pipes. We can conclude that the friction coefficient decreases steadily when the Reynolds number increases. This is due to the influence of the surface roughness and the size of pipe diameter. So higher surface roughness and internal diameter of pipe lead to higher coefficient of friction.